2.11 is a very, I would say, mathematically tedious problem because we have to do a lot of integrals. Specifically, we have to do 8 different integrals to calculate the expectation values of x, p, x squared, and p squared for psi naught and psi 1 of the harmonic oscillator. Because of that, I'm going to split this into, instead of doing this A, B, and C, I'm going to do A, B, and C for psi naught first, and then we'll do it again for psi 1. A lot of the integration, and pretty much like 90% of our time is going to be spent doing part A for both psi naught and psi 1. So I am going to sort of speedline the process a little bit by sort of skipping over techniques that we've gone over already before. But other than that, this is really just sort of a plug and chug, so let's get right to it. We are asked to compute the expectation values of x, p, x squared, and p squared for the states psi naught and psi 1. For now, we will focus only on psi naught and ignore psi 1. And then we'll do A, B, and C for psi naught, and then cycle back to psi 1, as I've said earlier. Our hint is that typically for harmonic oscillator problems, the math is simpler if we introduce this variable that's called psi, xi in this case, and we are to define it as x times the square root of m omega over h bar, and we also want to introduce a constant alpha equals m omega over pi h bar to the 1/4. So before anything else, let's start by defining our psi naught and psi 1 wave functions. We already know what they are. Psi naught was given to us at the start of this section when we derived it for the harmonic oscillator, and we found psi 1 in example, I believe it was 2.4. So if we write these out first off before anything, then we know that psi naught is equal to m times omega, over pi h bar to the power of 1/4, multiplied by the exponential e to the power of negative m omega over 2h bar, and then multiplied by x squared. And then we also have the first wave function, the first excited state, psi 1, which is going to be equal to this same m omega over pi h bar to the 1/4 term, multiplied by square root of 2m omega over h bar, multiplied by x times e to the power of negative m omega over 2h bar times x squared. And first things first, before we actually do anything, let's try to redefine these in terms of these two suggested variables. So immediately, we have alpha here, and this is just alpha to the 1/4, so we can immediately sort of replace this with alpha. So if we know that alpha equals omega, m omega to the 1/4, we can just replace alpha at the front for both of these and write this as alpha multiplied by this term. Next, we have the psi term, which is equal to square root of m omega over h bar times x. Immediately, you should see that we can sort of convert it here, this way. So let's see. We have a, so psi, this is very hard to draw. I'm actually going to, instead of drawing psi, I'm going to draw it as y instead, because this is quite frankly impossible for me to draw well, especially on mouse. Maybe on pencil would be better, but for now, let's define it this way as y is equal to the square root of x times, y is equal to x times the square root of m omega over h bar. So we see here that we have an x squared, so let's try squaring y and seeing what we get. So y squared is going to be equal to x squared times m omega over h bar. What we have here is m omega over h bar times x squared, but divided by an extra 2, so we can automatically rewrite this as negative y squared over 2. And we can do the exact same thing over here as well. Next, we have this extra x term that we might want to get rid of because we're trying to define all of the x's in terms of the size. So if we sort of switch this around, then we get that x is actually equal to the square root of, or y times the square root of h bar over m omega. So if we write it like that, you should immediately we should see that we have square root of h bar over m omega, and we have square root of m omega over h bar. So those automatically cancel. The square root of 2 remains, and we have alpha times y times square root of 2 multiplied by e to the negative y squared over 2. And this is the actual psi naught and psi 1 that we want to work with, assuming that we're following Griffiths' hint and sort of redefining everything in terms of these two variables. So now we can actually go on and find the expectation values. For the expectation value of x for psi naught, we can write this, as we've seen before many times, as expectation value of x for, let's call it x naught to represent the 0th state or the ground state expectation value for x. This is going to be equal to the integral from negative infinity to infinity of psi naught star times x, because the operator for x is just x itself, times psi naught dx. And in this case, since psi naught doesn't have any imaginary terms, its complex conjugate is exactly equal to its real variant. So because of that, we can just write this as alpha squared times the integral from negative infinity to positive infinity of e, and then we have e to the negative y squared over 2 squared, so e to the negative y squared over 2 times 2, so that just becomes e to the negative y squared, and this is multiplied by x dx. And as Griffith said before, it's better if we work in terms of this y variable instead of x, so let's do sort of a variable substitution here. We know that x, we sort of have this relation over here already, that x equals y times square root of h bar over m omega. If we derive this, then we can also get that dx is equal to dy times the square root of h bar over m omega. So if we substitute both of these sort of things into our integral here, then we get that this is equal to alpha squared times, and we have x contributing a factor of square root of h bar over m omega. We have dy contributing also, or dx also contributing to a factor of square root of h bar over m omega. So we get alpha squared times h bar over m omega multiplied by the integral. The integral bounds remain as negative infinity infinity because x and y sort of share a linear relationship. So if x goes to negative infinity, this is a constant, so y also has to go to negative infinity, same for positive infinity. So the integral bounds are still from negative infinity to positive infinity. And then we have e to the negative y squared times y times dy. And this looks like a Gaussian, but it actually, in this case, it isn't. We can take advantage of sort of the derivative form of e to the negative y. So if we recognize that d by dy of e to the negative y squared is equal to negative 2y times e to the negative y squared, then we have y times e to the negative y squared here. So what we can say is that y times e to the negative y squared is actually equal to negative d by dy of e to the negative y squared. So if we sort of replace that here, or actually there's a negative 1/2 here. My apologies, I made a mathematical error. This is let's see, move this to the right, and we have negative 1/2 times d by dy. Let me just make sure that's right. Negative 1/2. Yeah. So this term here, which is this, is actually equal to negative 1/2 d by dy e to the negative y squared. So this can be rewritten as negative alpha squared times h bar over 2m omega times this integral from negative infinity to positive infinity of 1/2 times d, whoops, the 1/2 is already incorporated, d by dy of e to the negative y squared times dy. And this is a derivative of an integral, so that cancels out, and we get that this is equal to negative alpha squared h bar 2m omega multiplied by e to the negative y squared, evaluated from y equals negative infinity to y equals infinity. And this is very obviously 0, because y squared, infinity squared, and negative infinity squared both equal infinity, and e to the negative infinity is just 0. So the expectation value of x is just equal to 0. And we have solved the first of 8 integrals. Okay, we found x naught. Now we want the expectation value for x squared for the psi naught state. So expectation value of x squared naught is going to be equal to, and we take the same form as before, so the integral from negative infinity to positive infinity. And since psi naught is a real function, we just, instead of writing this out all formally as psi naught star times x squared times psi naught, we can just write this as psi naught squared times x squared dx. And then if we expand this, psi naught has this alpha term at the front, which becomes alpha squared times the integral from negative infinity to infinity of x squared, and then we have e to the negative y squared half squared, so this is just e to the negative y squared dx. Once again, we use this sort of change of variable term, so this ends up with x squared contributing a factor of h bar over m omega. Dx contributes another factor of square root of h bar over m omega, so we get a total of alpha squared times h bar over m omega to the 3/2. This is a horrible exponent writing, I'm sorry. Multiplied by the integral from negative infinity to infinity of y squared times e to the negative y squared dy. And this is something that we've encountered many times before. I'm just going to speed through this because this is something that was covered in a previous problem. But effectively, we use integration by parts. We take advantage of integration by parts by sort of recognizing that d by dy of e to the negative y squared is equal to negative 2y times e to the negative y squared dy. Or I'm just not going to add the dy here, but we can rearrange this and we get that y times e to the negative y squared is equal to negative 1/2 times d by dy of e to the negative y squared. So we can rewrite this as the expectation value of x squared in the psi naught state to equal the same constant terms at the front, so alpha squared h bar over m omega to the power of 3/2, but this time evaluated an integral from negative infinity to infinity of y multiplied by negative 1/2 times d by dy of e to the negative y squared dy. So we can move the negative 1/2 over to the other side, so this becomes negative alpha squared over 2. Get this out and then move everything over. So we're left with this. Then we use integration by parts. So if we say that u is equal to y, then du is equal to dy, and dv is equal to d by dy of e to the negative y squared dy. Then v itself is equal to e to the negative y squared. Then we use uv minus integral v du. Uv is y times e to the negative y squared, evaluated at positive and negative infinity. The exponential goes to 0 exponentially fast, whereas the y term goes to infinity linearly. So because of that, automatically the exponential always wins, and the boundary term goes to 0. What we're left with is x squared, evaluated for the ground state psi naught term being equal to negative alpha squared over 2 times h bar over m omega to the power of 3/2 times the integral, let's see, so uv is 0 minus integral of v du, so minus the integral from negative infinity to positive infinity of v du, which is e to the negative y squared dy. And this is just the Gaussian integral. So this equals alpha squared. So we're going to cancel out the negatives. So this is sort of the same thing as before. So I'm just going to copy paste this. Alpha squared over 2 times h bar m omega to the power of 3/2 multiplied by the integral from negative infinity to positive infinity of e to the negative y squared dy. So at this point, this is just the Gaussian integral, which we solved back in like chapter 1. I believe it was problem 1.3. But yeah, this is at this point, hopefully these integrals are pretty trivial. If not, you can always just sort of throw them into an integral calculator and do them for you. The reason why that we're sort of just glossing over this is because Griffiths is an intermediate textbook. If you are taking this for college, typically I believe that finals will tend to just give you sort of Gaussian integral formulas. You're not really expected to memorize how to solve this. Granted, it is useful and you definitely should, because I believe that once you get to graduate level classes, you will be expected to know this by heart. Just as a quick reminder, sort of as a quick digression, I'm going to mention this once, and then every time we encounter this again for the rest of this video, I'm just going to skip over it. But this can be rewritten as an integral from negative infinity to 0 of e to the negative y squared dy plus the integral from 0 to infinity of e to the negative y squared dy. We can then add a negative here at the front of this first integral and change, or like reverse the bounds, so that we go from, instead of negative infinity to 0, we go from 0 to negative infinity. And this just becomes sort of, because we know that ERF of z is equal to 2 over the square root of pi times the integral from 0 to z of e to the negative y squared dy. Let me just double check this to make sure that my constants at the front aren't wrong, because embarrassingly enough, I also do not tend to remember the general form for the ERF function. 2 over the square root of pi. Yes, I am correct. Okay. So because of that, then the integral from 0 to z of e to the negative y squared dy is equal to square root of pi halves times ERF of z. So this allows us to sort of rewrite this whole thing. Let me just move this into a slightly better position. So this sort of allows us to sort of rewrite these two expressions as negative root pi over 2 of ERF negative infinity plus root pi over 2 of ERF of positive infinity. And the error function of plus minus infinity is plus minus 1 respectively, so this is just actually equal to square root of pi. So because of that, this integral is just square root of pi, because we have negative square root of pi over half times negative 1 plus square root of pi over half times positive 1. So that's just 2 times square root of pi over 2, which is just square root of pi. So we write this out fully. X squared expectation value evaluated at psi naught is going to be equal to the same constants at the front again of alpha squared over 2 times this h bar blah 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 term, and then we're multiplying it by another square root of pi. And this is technically the answer. However, we can simplify this and make it a little bit nicer if we sort of re-plug back in our alpha term. So we know that alpha equals m omega over pi h bar to the 1/4. So alpha equals, I forgot, m omega over pi h bar to the 1/4. So alpha squared is just this square root of m omega over pi h bar. So this is actually equal to 1/2 times the square root of m omega over pi h bar multiplied by h bar over m omega to the 3/2 times the square root of pi. Immediately, we see that the square root of pi here cancels with the square root of pi at the bottom, leaving only square root of m omega over h bar. Square root of m omega over h bar is just m omega over h bar to the 1/2. We have h bar over m omega to the 3/2. So 3/2 minus 1/2 is just 1. So this is actually equal to just h bar over 2m omega. And that is our answer for our second of 8 integrals. Next, let's do the expectation value for p in the ground state. So we know that p hat is equal to -I h bar d by dx. So in this case, we actually will have to write out the full formal expectation value formula, in that the expectation value of p is going to be equal to the integral from -infinity to infinity of psi naught. And let's also write the naught here to indicate we're finding p, or the expectation value of p for the ground state. So psi naught star times -I h bar d by dx of psi naught dx. We write this out fully, then we get, so the alpha, or the alpha terms for psi naught at the front come out just like before. We also have this -I hat, or -I h bar term. So -I h bar times alpha squared times the integral from -infinity to +infinity. And we have psi naught star, which is equal to psi naught. So this is e to the -y squared halves multiplied by d by dx of e to the -y squared half times dx. Okay, so this is a d by dx, but our exponential is in terms of y. We can use chain rule, or we can just brute force it. Personally, I kind of prefer brute forcing it, so that's exactly what I'm going to do. We're going to instead, so what I'm going to do is I'm going to rewrite this in terms of x. So d by dx of e to the power of -m omega over 2h bar times x squared. So the derivative of this is going to be equal to -m omega over h bar times x times the same exponential, which I'm going to rewrite back as -y squared over 2. So that means that the expectation value of p in the psi naught state is going to be equal to, let's see, so we have this new negative term that cancels out the negative at the front. So we have I h bar times alpha squared times m omega over h bar times the integral from -infinity to +infinity. And now we have this x term, which I'm going to move to the front, and we have e to the -y squared half multiplied by the e to the -y squared half that was at the beginning. So this becomes e to the -y squared dx. And at this point, we do another change of variables to go from x to y. So each x and dx term respectively adds a square root of h bar over m omega factor. So we have an x and a dx. So this is equal to I times h bar times alpha squared times m omega over h bar. And then we have the two factors of square root of h bar over m omega, which just becomes h bar over m omega. So these two automatically cancel because they're reciprocals. They just become 1. We can just ignore them. And then our integral from -infinity to +infinity of y times e to the -y squared dy. And hopefully this looks sort of similar to when we calculated the expectation value of x in the psi naught state. We can sort of, I've already done this once, so I'm not going to do it again, but this integral is going to be equal to 0, and the way we solve it is we take advantage of the fact that we can write d by dy of e to the negative y squared to be equal to negative 2y times e to the negative y squared. Then we just rewrite this y e to the negative y squared in terms of d by dy, cancel out the integral, and we get an exponential e to the negative y squared evaluated at plus minus infinity, in which case they're both equal to 0, so this integral just equal to 0. Therefore, the expectation value of p in the psi naught state is also equal to 0, and that is integral 3 of 8. Let's do the exact same process again for p squared. We know that p hat is negative I h bar d by dx, so applying it a second time, we have p hat squared is going to be equal to, the two negatives make a positive, but the I times I makes a negative, so negative h bar squared times d2 by dx squared. Applying this, the expectation value of p squared in the psi naught state is going to be equal to negative h bar squared times the integral from negative infinity to positive infinity of psi naught star, which is exactly equal to psi naught, so I'm just going to write this as psi naught, multiplied by d2 by dx squared of psi naught dx. Once again, this is an x derivative. We've written psi naught initially in terms of y, so I'm going to rewrite it in terms of x to sort of brute force out this derivative. We have negative h bar squared, and then we have the alpha terms that come out at the front, so alpha squared times the integral from negative infinity to positive infinity of e to the negative y squared half multiplied by d2 by dx squared of e to the negative m omega over 2h bar times x squared dx. So this term is going to come out to equal d by dx of, let's see, d by dx of negative m omega over h bar times x multiplied by e to the negative m omega over 2h bar x squared. So if we substitute this back into our integral, then we have the expectation value of p squared at psi naught is equal to, let's see, the two negatives make a positive, so we have h bar squared times alpha squared times m omega over h bar times the integral from negative infinity to infinity of e to the negative y squared over 2 times d by dx of x times e to the negative m omega over 2h bar times x squared multiplied by dx. Let's do some cancellation here. We have an h bar squared at the top that cancels out the h bar at the bottom, so we're just left with m omega. Now let's derive a second time to get the answer for this. So we use integration by parts here. So this becomes e to the negative m omega over 2h bar times x squared plus x times negative m omega over h bar times x times e to the negative m omega over 2h bar x squared. Okay, rewriting this, we're not going to derive this anymore, so we can turn the e term back in terms of y, so this becomes e to the negative y squared over 2 times 1 minus m omega over h bar times x squared. Is that correct? Yes, that's correct. And we plug that back in and we get that the expectation value of p squared in the psi naught state is going to be equal to h bar alpha squared m omega times our integral from negative infinity to infinity, and then we have one e to the negative y squared half term here, and we have the other e to the negative y squared half term at the front, so that becomes e to the negative y squared And then we have this extra term of 1 minus m omega over h bar times x squared times dx. And now we just split this into two integrals. So this is going to be equal to the integral from negative infinity to positive infinity of e to the negative y squared dx subtracted by m omega over h bar times the integral from negative infinity to infinity of x squared e to the negative y squared dx. And now we convert our x's back to y's. So each x term contributes square root h bar over m omega. Each dx term also contributes square root of h bar over m omega. So this is going to become, let's see, in this case there's only one thing. So square root of h bar over m omega. Is that it? H bar over m omega, yeah. Times our integral from negative infinity to positive infinity of e to the negative y squared dy minus, and here we have two x terms and one dx term, so this is minus m omega over h bar times h bar over m omega to the 3/2. So these cancel out, so this is 3/2 minus 1, which is just going to give us 1/2, so this entire thing is actually just equal to square root. This is minus square root h bar over m omega times the integral from negative infinity to positive infinity of y squared times e to the negative y squared times dy. And once again, these are ERF functions, so we know that sort of the error function of z is equal to, I believe, 2 at the top, yes, 2 over square root of pi times the integral from 0 to z of e to the negative y squared dy. So this can be rewritten here. So we have what we really have here. Let's move this like over here. Yeah. Okay, so what we really have for term 1, so let's write this in red. So this is an integral, this is a negative integral from 0 to negative infinity of e to the negative y squared dy plus an integral from 0 to infinity of e negative y squared dy. So this is actually just equal to, let's see, square root of pi over 2 times, and this is negative ERF of negative infinity, which is just negative times negative 1, which is positive 1, plus the ERF of infinity, which is just 1 again, so this is just 1 plus 1, so this equals the square root of pi. Now, for this green term, we have to use sort of the same thing we've been using before, which is the whole integration by parts procedure. So d by dy is equal to, or d by dy of e to the negative y squared is equal to negative 2y times e to the negative y squared. So that means y times e to the negative y squared is equal to negative 1/2 d by dy of e to the negative y squared. We plug this all in, so this is going to be an integral from negative infinity to positive infinity of y multiplied by negative 1/2 at the front times d by dy of e to the negative y squared. Then we use u sub, just like before, so we know that u equals y, then du is going to equal dy, and then dv is equal to d by dy. I don't even know why I'm writing this when I can just copy paste it. And then v is equal to the integral of this, which cancels out the derivative. So this is v is just equal to e to the negative y squared. We have uv minus integral v du. This v term cancels out the border term because v goes to 0 faster than y, then u goes to positive or negative infinity. So the boundary term goes to 0. We have negative 1/2 of uv, which is 0, minus integral of v du, so minus the integral from negative infinity to positive infinity of e to the negative y squared times dy. Then we rewrite this, so this is another ERF function, and as we've seen up above, this is exactly equal to the red, negative infinity to infinity of e to the negative y squared dy. So this is just going to be equal to the square root of pi. So this whole thing is going to be equal to square root of pi over 2. We plug everything back in, and we get that the expectation value of p squared in the psi naught state is going to be equal to the same constant we have at the front, which is h bar alpha squared m omega. And then multiplied by this integral, which we've seen is equal to the square root, because both of these terms have a square root h bar over m omega at the front. And then we have this red term, which is square root of pi, subtracted by this green term, which turns out to be square root of pi over 2. So these two just become square root of pi over 2. This gives us alpha squared h bar m omega over square root h bar over m omega times square root of pi divided by 2. And now we rewrite this, plugging in alpha equals 1/4 power of m omega over pi h bar. So this equals the square root of m omega over pi h bar. So square root, because alpha squared, m omega over pi h bar times h bar m omega times square root of h bar over m omega times square root of pi divided by 2. So the square root of pi automatically cancels out with the square root of pi at the bottom. So this becomes 1/2. And the square root of pi cancels out, so we have square root of m omega over h bar. That cancels out with square root of h bar over m omega, so these two go to 0, and our final result is 1/2 h bar times m omega. And with that, we have finished the first 4 integrals out of 8. Okay, in part B, we're asked to check the uncertainty value for all of these states. So the uncertainty principle, which we learned back then, was that the uncertainty of x multiplied by the uncertainty of p has to be greater than or equal to h bar over 2. And what we're being asked here is to verify that this is true for both the psi 0 and psi 1 state. We'll do the psi 1 state later. We just got the psi 0 state, so let's do that first. We know that the uncertainty for any observable thing, A, let's call it, from chapter 1, when we did this, we found that the formula for the uncertainty in any observable is equal to the square root of the expectation value of that observable squared, subtracted by the expectation value of that observable itself squared. So let's find the uncertainty in x first. So this is equal to the square root of the expectation value of x squared minus the expectation value of x by itself, then squared. We found already that the expectation value of x by itself squared is just 0, so this is just equal to the square root of expectation value of x squared, which is then going to be equal to square root of h bar over 2m omega, because we just found that the expectation value of x squared is h bar over 2m omega, so we just take the square root of that. Doing the same thing with p gives us that the uncertainty in p is equal to the square root of expectation value of p squared minus the expectation value of p itself squared. And we also know that the expectation value of p is equal to 0 in the ground state, so this also goes to 0, so this is just equal to the square root of the expectation value of p squared. This is going to be equal to, so the expectation value that we found is 1/2 h bar m omega, so this is going to be equal to the square root of 1/2 h bar m, or whoops, sorry, 1/2 h bar m omega. So if we then multiply these two together, then standard deviation, or uncertainty in x times uncertainty in p, is going to be equal to the square root of h bar over 2m omega times 1/2 over h bar m omega. Immediately, we see that the m omega terms cancel. We also have h bar, so then we have h bar squared over 2 squared. So this is just going to be equal to h bar over 2. And that is exactly equal to the minimum amount required. So we see that the ground state wave function has sort of the smallest product of uncertainties. And with that, we are done with part B, and we can move on to part C. Finally, in part C, we're asked to compute the expectation values of kinetic and potential energy for psi naught and psi 1 without using explicit integration. And then we're asked to see whether or not the resulting sum is what we would expect. So without doing integration, what that implies is that we're supposed to use the results we got here. And indeed, it is possible to sort of just plug and chug our results in, because let's start with the potential energy. So we know that for a harmonic oscillator, V is going to be equal to 1/2 times k x squared, or in terms of omega, because we were told that writing in omega makes everything easier in quantum mechanics, this is equal to 1/2 m omega squared x squared. And everything here at the left is a constant, only variable is x. So if we were to find the expectation value of V, this is really just 1/2 times m omega squared times the expectation value of x squared. We already have this from earlier. This is equal to h bar over 2m omega. So this is equal to 1/2 times m omega squared times h bar over 2m omega. The m's cancel, the omega squared goes to omega, and we get h bar, get h bar times omega over 4. Now, we do the same thing for t. We know that kinetic energy is equal to 1/2 mv squared, but we also know that one of the things Griffiths told us earlier on is that instead of working with velocity, it's better to work with momentum in quantum mechanics. So using the fact that p equals mv, we can rewrite this as p squared over 2m. Once again, 2m is a constant, p squared is the only variable, so the expectation value of t is going to be equal to 1 over 2m times the expectation value of p squared. We also have this from earlier. It's equal to 1/2 h bar m omega. So this equals 1 over 2m times 1/2 h bar, 1/2 h bar m omega. So 1/2 h bar m omega. So then this becomes, the m's cancel. We get 1/4 h bar omega. And if we add them, the sum of the expectation values of kinetic and potential energy is going to be equal to h bar omega over 4 plus h bar omega over 4, which is just 1/2 h bar omega. And if we remember the energy values for the quantum harmonic oscillator, we solved for that earlier on in the actual chapter itself, and we know that the energy values are equal to En equals n plus 1/2 times h bar times omega. So the energy of the ground state, E0, is just going to be equal to 1/2 h bar omega, which is exactly what we get here. So yes, they are in fact sort of the sum that we get is in fact what we would expect. And with that, we are complete with one half of this problem. We now have to do everything all over again for the psi1 state. Okay, let's sort of do this tedious process all over again for psi1. So we know that psi1, we've written it out in terms of alpha and y. Let's start right away with just x. So the expectation value of x in the first excited state is just going to be equal to the integral from negative infinity to infinity of psi1 squared, because once again, psi1 is a real function and it doesn't have any imaginaries for the complex conjugate to actually turn into negatives with, multiplied by x times dx. So if we take the squared term of psi1, we get alpha squared, or we have a root 2 and we have an alpha. So at the front, it becomes 2 alpha squared times the integral from negative infinity to positive infinity. And then we have y squared times, we have y squared multiplied by x times e to the negative y squared dy. If we then do a switch of variables from x to y, we have, this is dx, not dy. We have an x term and a dx term. Both of these contribute a square root of h bar over m omega. So this becomes equal to 2 times alpha squared times h bar over m omega times the integral from negative infinity to infinity of y cubed times e to the negative y squared dy. And this is pretty much the same song and dance that we've done for the previous 4 integrals. We just use the whole idea of like mashing one of these 3 y terms into the e and turning it into a derivative of e to the negative y squared, and then using integration by parts, going down, and that'll result in y squared e to the negative y squared. We do it all over again, blah, 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 blah. This integral turns out to be 0. In order to sort of save time for myself, I'm not going to go through the trouble of doing this all over again, because the process for solving this is quite literally exactly the same as the previous 4 integrals. So this gives us our first integral sort of our final 4. Doing the whole song and dance again for x squared, the expectation value of x squared in the first excited state is going to be equal to the integral from negative infinity to positive infinity of psi1 squared times x squared times dx. And then we write everything out again. So we have 2 alpha squared at the front as a constant, because we have alpha and we have root 2, and those are getting squared. And then we have our integral from negative infinity to positive infinity of y squared times x squared times e to the negative y squared over 2 times dx. Once again, we convert, so we have all the x terms contributing and all the dx terms contributing this factor of square root of h bar over m omega. We have 2 x terms and 1 dx term, so we're going to have h bar over m omega to the power of 3/2. We have 2 alpha squared times h bar over m omega to the power of 3/2 times the integral from negative infinity to positive infinity of y, this time to the 4th, times e to the negative y squared over 2 times dx, or dy this time. And my apologies, this is not y squared over 2, this is actually y squared, because y squared over 2 squared is just y squared. And now we are left with, once again, the same pattern as before. So the way we do this, as it turns out, for the excited state of psi1, we're doing sort of the exact same process, but only we have to iterate it multiple times. If we do the integration by parts by sort of mashing one of the y's into the e, this is going to bring y down to y squared times e to the negative y squared with a few constants at the front. Then we do it all over again a second time to finally get rid of the integral. This is, once again, a very tedious thing, and I really don't want to waste my time doing this when we've already sort of covered the general method for how to do this for the psi naught expressions. So I'm just going to leave you with the answer for this, which I'm going to get by plugging into my calculator, and it's going to equal 3 h bar over 2 m omega. You should definitely try this if you feel like you're still rusty with using Gaussians and sort of just generally trying to solve integrals of this nature. But if you feel comfortable with it, then by all means skip it, because this is really just more of the work we did in sort of the first part when we were doing this entire thing for sort of the ground state wave function. Now let's do P again. So the expectation value for P in the first excited state is going to be equal to the integral from negative infinity to infinity of psi 1 times negative I times h bar times d by dx times psi 1. Once again, we're just foregoing the complex conjugate star term because psi 1 is a real function here and it doesn't have any imaginaries for us to actually turn into negatives. So its complex conjugate is exactly just equal to its real component. We add the dx at the front. Move everything over. This becomes negative I h bar times the integral from negative infinity to positive infinity of psi 1 times d by dx of psi 1 dx. Okay, write everything out. The alpha and root 2 get squared, so we get negative 2 I h bar times alpha squared. And then we have the integral from negative infinity to positive infinity of y times e to the negative y squared over 2 times d by dx of this same term, y times e the negative y squared over 2 dy, or dx in this case, my apologies. And then we have to do this integral, so I'm going to brute force it by converting back into x. So let's see, this is going to be d by dx of, we know that y equals x squared root of m omega over h bar, so x, so square root of m omega over h bar times x, and then times e to the negative m omega squared over 2 h bar times x squared. Let me just make double sure that that's the correct format. E to the there's no squared on omega, my apologies. So negative m omega over 2 h bar times x squared. And then we just do integration by part, or chain rule, my apologies, for derivatives. So this becomes square root. We move the constant out to the front, so square root of m omega over h bar comes to the front. And then we have e to the negative, and we're going to move this, we're going to convert this back in terms of y, so e to the negative y squared over 2 plus x times negative m omega over h bar times x, and then e converting back to y, negative y squared over 2. So this is equal to e to the negative y squared over 2 times the square root of m omega over h bar multiplied by 1 minus m omega over h bar times x squared. And then we plug this back into our integral. So this is going to give us, let's see, the expectation value of p in the first state is going to be equal to negative 2, the same constant at the front, so negative 2 I times h bar times alpha squared. My mouse is starting to break, so apologies for this very messy handwriting. But then we move this constant over here, so this becomes square root of m omega over h bar. And then we have our integral from negative infinity to positive infinity. And then we have y times e to the negative y squared over 2. And then we're multiplying by another e to the negative y squared over 2. And then we're multiplying by this 1 minus m omega over h bar times x squared dx. So if we combine everything, this is going to become sort of the same constants at the front. So 2i times h bar alpha squared times the square root of m omega over h bar, and then multiplied by the integral from negative infinity to positive infinity of, let's see, y times e to the negative y squared dy minus m omega over h bar times the, or not dy, but dx, times the integral from negative infinity to positive infinity of y times x squared times e to the negative y squared dx. And then we do the same process of converting from x to y. So every x and dx term contributes this factor of square root of h bar over m omega. So in this case, there's exactly 1. In this case, there's 3. So then this gives us 2i h bar alpha squared times square root of m omega over h bar. And then this is multiplied by, let's see, square root of h bar over m omega times the integral from negative infinity to positive infinity of y times e to the negative y squared times dy, and then minus m omega over h bar. And then there's 3 of these, 2 x's and like 1 dx. So this gives us an h bar over m omega to the power of 3/2. And then this is directly a reciprocal of m omega over h bar, so 3/2 minus 1 is just 1/2. So this really just gives us a square root term. So this is equal to minus the square root of h bar over m times omega times the integral from negative infinity to positive infinity of y cubed times e to the negative y squared times dy. And then we factor out these square root of h bars over m omegas, which cancel with the square root of m omega over h bars. And then we get, finally, this. And then let's move sort of everything over. And once again, exact same process for solving these Gaussian integrals. I do not want to do this all over again, so I'm just going to give you what they should equal. Feel free to evaluate them if you feel like you need the practice. Both of these are going to be equal to 0. And as it turns out, in general, for any form, when we have something of the form of negative infinity to infinity, of like sum of a variable x to the nth power times e to the negative x squared dx, when we have a Gaussian of this form, in general, if n is an odd number, this integral is always going to be equal to 0. And the reason why is because e to the negative x squared is an even function. And so if we have an odd number of n, then x to the power of n is going to be an odd function. So an odd function times an even function is going to be an odd function. And a symmetric integral of any odd function is always going to be 0. So because of that, these two integrals both equal 0. And our third integral for the expectation value of p is going to be equal to 0. Finally, our last integral, and it has been a very sort of tedious process to get here, the expectation value of p squared. So expectation value of p squared in the first excited state is going to be equal to the integral from negative infinity to infinity, again, of psi 1 times, and then negative h bar squared d by dx squared, so d2 by dx squared of psi 1 times dx. move everything out to the side, and then express everything, and we get negative h bar squared, and then we have 2 at the front, and then the alpha squared term, and then we have our integral from negative infinity to positive infinity of, let's see, this is going to be y times e to the negative y squared over 2 times the second derivative d2 by dx squared of y times e to the negative y squared over 2. And just by looking at this, it already makes my skin crawl because this is a very tedious integral. Let's just do it. So this is, we're gonna convert this into x. So d2 by dx squared, y is equal to x times square root of m omega over h bar. So square root of m omega over h bar times x times e to the negative m omega over 2h bar times x squared. And then we move this square root of term out to the left, and we get square root of m omega over h bar, and then multiplied by this thing, which is going to be d by dx, because we're only doing one derivative. Using chain rule, this is e to the negative m omega over 2h bar x squared plus x times negative m omega over h bar times x times e to the negative m omega over 2h bar x squared. If this is getting very tedious, then that's a good thing, because that means that you do have the amount of practice that's necessary. So take hope in that if you are very bored at this point and don't want to do this any longer. Anyway, we can take square root m omega over h bar, same thing, d by dx. Let's do sort of a, what do we call it? Let's do a bit of a, let's make this a little bit nicer. So e to the negative m omega over 2h bar times x squared minus m omega over h bar times x squared times e to the negative m omega over 2h bar times x squared. Let's use distributive property to make this simpler. So same square root over m omega h bar d by dx, this time of e to the negative m omega over 2h bar times 1 minus m omega over h bar x squared. Take the integral of this, we get square root m omega over h bar. Let's see. Using chain rule, this is, whoops, I left out an x squared here. So this is going to be negative m omega over h bar times x. There's no more derivatives, so we can convert back to y. So e to the negative y squared over 2 times 1 minus m omega over h bar times x squared. And we're adding this with e to the negative y squared over 2, and then this time taking the derivative of the other side. So this is 1 goes to 0, and then we have, let's see, negative 2m omega over h bar times x. Then we factor out the e term, so this gives us e to the negative y squared over 2 times square root of m omega over h bar, and multiplied by negative m omega over h bar times x, multiplied by 1 minus m omega over h bar x squared, plus, or in this case minus, 2m omega over h bar times x. So immediately we can take out an m omega over h bar, so this becomes e to the negative y squared over 2 times square root of m omega over h bar, multiplied by m omega over h bar. This gives us negative x times 1 minus m omega over h bar times x squared minus 2x. Get this out more, and let's see, this is going to give us this, which we can sort of simplify as m omega over h bar to the power of 3/2. Is that correct? 1/2, 2 over 2, yeah. And then negative x minus 2x plus m omega over h bar times x cubed, or just condensing these two x terms, this is negative 3x. And now we plug this back in. So let's see. We're plugging it back into here. So this is the expectation value of p squared in the first state is going to be equal to negative 2h bar squared alpha squared and then our integral from negative infinity to infinity, and then we have y, and then the two exponentials combine to make e to the negative y squared, and then the remaining terms, which is m omega over h bar to the power of 3/2 multiplied by negative 3x plus m omega over h bar x cubed. And then follow that off with a dx. Okay, let's move this out because it's a constant, and then let's split this into two integrals. This becomes negative 2 h bar squared alpha squared times m omega over h bar to the power 3/2. Hopefully by my writing you can tell that my patience is getting very close to the end for this problem. But this is going to be equal to the integral from negative infinity to infinity of, let's see, negative 3x times y times e to the negative y squared dx plus the integral from negative infinity to infinity of m omega over h bar x cubed times y, and then e to the negative y squared dx. Let me just double check that everything is correct. Yes, everything should be right at this point. And from that point on, we just have to do the same integrals all over again. So let's start by sort of converting these both to dy. So we know that all the x terms and all the dx terms convert with factors of square root of h bar over m omega. So this equals the same constants at the front multiplied by, let's see, here we have one x term and one dx term, so we get a factor of h bar over m omega. So negative 3 times h bar over m omega times our integral from negative infinity to positive infinity of y squared e to the negative y squared dy, and then added with, and let's see, we have m omega over h bar, and then we have 3 x terms and 1 dx term, so this is going to be times h bar over m omega squared, and these two will cancel out, so we just get h bar over m omega. Times the integral from negative infinity to positive infinity of y to the 4th times e to the negative y squared times dy. And just like that, we have a common factor that we can sort of get rid of with the m omega over h bar here. So this becomes -2 h bar squared, alpha squared, and then the 3/2 cancels with the 1 power. So this becomes square root of m omega over h bar. And then -3 times our integral from -infinity to +infinity of y squared e to the -y squared times dy plus our integral from -infinity to +infinity of y to the 4th e to the -y squared dy. The method we use to solve these are both the same. We've done this earlier for the psi1 terms. The method for solving this is the exact same. We do the same sort of u sub method, and y to the 4th will get dropped down to y squared. We do it a second time, and then that actually solves the integral. So this is pretty much doing the same technique 3 times in a row. So once again, I'm going to skip this really tedious part and just get straight to the answer, which turns out to equal 3/2 times m omega times h bar. And with that, we are thankfully done with all 8 integrals. All right, we are on the final stretch. Let's start by doing part B, which is to find sort of the uncertainties in x and p, and then verify that the uncertainty principle is in fact still true. So standard deviation in x, or the error in x, is equal to the square root of expectation value of x squared minus the expectation value of x itself squared. Since this expectation value of just x itself is 0, then this is going to be equal to the square root of 3 h bar over 2m omega. By the same logic, the standard deviation in p is going to be equal to the square root of 3/2 times h bar m omega. If we take the products, then the standard deviation of x and standard deviation of p is going to be equal to the square root of 3/2 h bar m omega over h bar over m omega multiplied by 3/2 times h bar times m omega. So the m omegas cancel, and we get 3/2 h bar, which is indeed greater than the minimum required value, which is 1/2 h bar. Next, we want to find t and v. So we already know the formulas from before. The expectation value of v is going to be 1/2 m omega squared times the expectation value of x squared. We know what this is, so this is going to be equal to 1/2 times m omega squared times the expectation value of x squared, which is 3h bar over 2m omega, so times 3 h bar over 2m omega. The m's cancel, the omegas cancel, and we're left with 3/4 h bar omega. Next, for t, this is equal to 1 over 2m times the expectation value of p squared. This is going to be equal to 1 over 2m. Then we know the expectation value of p squared is 3/2 h bar m omega, so 3/2 h bar m omega. The m's cancel, and we get 3/4 h bar omega. Adding the energies v and t gives us 6/4, also known as 3/2 h bar omega. And this is indeed what we expect, because remember, the energy formula is equal to n plus 1/2 times h bar omega. So the first excited state is going to have an energy of 3/2 times h bar omega, which is exactly what we have here. And we are done.